Given an n by n matrix A where each diagonal entry is n and all off diagonal entries are 1, find the eigenvalues of A. We have a matrix A, we have n along the diagonal, all off diagonal entries are 1, and we have to find the eigenvalues of this matrix. We can write this matrix as n minus 1 times the identity matrix I plus j, which is a matrix of all ones. If you think about it, if we have n minus 1 times I, this would give us a matrix where we'll have n minus 1 along the diagonal and all other entries would be 0, plus we have j, which would be a matrix of all ones. So when we add these together, the diagonal entries would all increase by 1, which would become n, and off diagonal entries will go from 0 plus 1 to 1. So this would give us this original matrix which we have. We can decompose this matrix into this form: n minus 1 times the identity matrix I plus j, which is the matrix of all ones. Now, the reason why we would want to decompose it like this is because we know the eigenvalues of the identity matrix, and we also know the eigenvalues of this J matrix, which is a matrix of all ones. Common fundamental rule is, which you'll find often useful, is if you have a matrix M in such a way that the rows of this matrix all sum to a value, say S, then in this case S is an eigenvalue of this matrix, and 1 1 1 dot 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 1 n times is an eigenvector of this matrix. Now if you use this rule for the identity matrix, we have the identity matrix, the diagonals are 1, all other off diagonal entries are 0. The sum of each row is 1, which means the eigenvalue of this matrix is 1, and the eigenvector is 1 1 1. Similarly, if you think about the matrix J which we have here, the matrix of all ones, we would have the sum of all rows of the matrix equal to n, which means that n is an eigenvalue of this matrix, and 1 1 n times is an eigenvector of this matrix. The other thing to remember is, if we have two matrices A and B, and these matrices have a common eigenvector, let's say V, so we can write this as AV equals to lambda 1 V, and BV equals to lambda 2 V. Now let's add these together. A plus B V equals lambda 1 plus lambda 2 times V. Now, what's this telling us? The sum of these matrices would have the eigenvalue equal to the sum of their individual eigenvalues. So this is another thing that you should remember, as it comes in useful, and as you'll see, this would be useful in this question as well. So now we have decomposed this into matrix n minus 1 I plus j. Now, what would be the eigenvalue of this part, and what would be the eigenvalue of this part? If we can find those, then as we just saw, the eigenvalue of the sum of two matrices is the sum of their eigenvalues. We can simply then add these eigenvalues together to get the eigenvalues of A. So let's look at the first part, n minus 1 times the identity matrix I. As we just discussed, if the rows of a matrix all add up to a number S, then S is an eigenvalue of that matrix. In this case, the rows would all add up to n minus 1, which means the eigenvalue of this part is n minus 1. So let me just write this here: n minus 1 times I and j on this side. The eigenvalue of this would be n minus 1, and for j, the eigenvalue is n. The eigenvalue of A would be the sum of these eigenvalues, which would be n minus 1 plus n is equal to 2n minus 1. But this is not the only eigenvalue. in the case of identity matrix, we have n eigenvalues. Each of them would be n minus 1. And in the case of this matrix J, we have one eigenvalue, which is n, and the rest are all 0. So we need to add all of these together. So we would have the first eigenvalue would be sum of these, this and this, which is 2n minus 1, and the remaining are all n minus 1. So here are more details. The eigenvalue of I are all 1. The eigenvalue of j and n, j are 1, n once and 0, n minus 1 times. J v equals n v because as we saw, if rows of j all add up to n, which means n is an eigenvalue, and the eigenvector would be 1, 1, 1 n times. So we have jv equals nv, where v the eigenvector is 1, 1, 1, and n is the eigenvalue. Jv equals 0 for v orthogonal to 1, 1 eigenvector. Since a is n minus 1 times I plus j, the eigenvalues of a are thus just the sum of these, n minus 1 plus n to n minus 1 for the eigenvector 1, 1, 1, and for eigenvector orthogonal to 1, 1, 1 would be n minus 1 plus 0 would be n minus 1. So this is the answer to the question.